Hi class, welcome back to Electromagnetics. So we're going to start part 5 of this course where we start to look at or continue our look at propagating electromagnetic waves, but this time instead of free space we're going to start looking at it in different types of media. Inspirational thought for today comes from Mark 16:15, and he said to them, "Go into all the world and preach the good news to everyone." So I thought this was appropriate because we have looked at the special case of uh, electromagnetic waves just propagating in free space. Now we want to go out from there and see what happens when we go into other mediums. So I think that's analogous to when we're in the church. We function as believers in the church, but we're called to go outside of the church into the world, into different mediums, and continue to advance the kingdom. So I don't know, I thought that was kind of an interesting parallel. So this starts part 5 of the course. Um, Again, we're looking at wave propagation in different materials, and so we're going to talk about conductors and dielectrics today. So we've now examined and have some understanding as to how electromagnetic waves propagate in free space, but now we want to look at what happens when an electromagnetic wave comes into contact with different type of materials medium. So some questions we might have is, will it continue to propagate in this new material? If it does propagate, how is it affected by this new medium? Or is it affected by this new medium? So these are a couple of the fundamental questions that we want to examine and try to understand in the next part of this course. So in this examination, we'll find that there are 3 main phenomena that occur in relation to electromagnetic waves and their interactions with charged particles. These 3 phenomena are conduction, polarization, and magnetization. So depending on which of these phenomena is predominant, that's going to determine what our material is classified as. And there's 3 types of material classifications when dealing with electromagnetic waves. If conduction is the predominant phenomena, then we would consider this medium to be a conductor. If polarization is the predominant phenomena, then it would be a dielectric. Some might refer to that as an insulator. And then finally, if the magnetic material is the predominant phenomena, then we would consider it a magnetic material if magnetization is the predominant phenomena. And so we want to look at all 3 of these. We'll do the first 2 today, and we'll look at the magnetic material next lecture. So in certain materials, a large number of electrons may participate in the conduction, while other materials only a few do. The first class is known as a conductor, while the latter class is known as a dielectric or an insulator. So if the number of free electrons participating in conduction is considered N sub E per cubic meter of material, the current density then is defined as this equation here. So we've got this number of electrons or number of participating electrons times the charge of an electron times this vector value of V sub D. Again, where E is the charge of an electron, this V sub D is the drift velocity, which we're going to define on the next slide. So the drift velocity varies from one conductor to another, conductor material to another, depending on the average time between successive collisions of the electron with the atomic lattice. So in general, it's related to the applied electric field as follows. So the drift velocity is equal to this mu sub E times the electric field. So this mu sub E, we refer to this as the mobility of the electrons. How mobile are they in this material? So if we substitute this into our previous equation, we now have our current density defined in terms of this mobility. So it's the mobility of electrons times the number of electrons times the charge of electrons times the electric field. So this is what's going to determine our current density. Semiconductors are characterized not just by the free electrons, but also the drift of holes, that is the vacancy of electrons. So we can extend this definition for current density to include that as well. So now, in addition to the mobility of electrons, we can have the mobility of the holes and the number of holes that are going to contribute to the current flow. So with this, we can now define the quantity in parentheses as the conductivity of the material. So this is formally then defined as, for conductors, the mobility times the number of electrons times the charge, and then for semiconductors we also add in the holes, the mobility of the holes and the number of holes participating. So with this new definition, we can now rewrite the original equation above as this, and so this is considered a constitutive relationship between the current density of the current that's flowing or conducting, that's equal to the conductivity times the electric field. So this now allows us to modify Ampere's law for materials as follows. So we've got the curl of the magnetic field is equal to our conducting current density plus the partial d with respect to the partial of the displacement current with respect to time. But we can replace this current density with the conductivity times the electric field. So just a new way to express or look at Ampere's law. So this conductivity is a value that we can measure for each material. So when we know we're dealing with certain materials, we can actually go to a CRC handbook or something and look these values up, or look them up on the internet. And so you can see that the higher the value, the better conductor this is going to be. So silver and copper and gold are excellent conductors, whereas you come down to distilled water, dry earth, glass, these things are not very good conductors, so their conductivity is pretty low by several orders of magnitude. So in dielectric materials, or what we consider non-conducting materials, the material's free electrons are not the predominant type. Bound electrons are. So in this case, under an external electric field, the bound electrons of an atom are displaced such that the centroid of the electron cloud is separated from the centroid of the nucleus. So in other words, instead of the electrons flowing, they will still want to line up with the electric field, so they'll start to pull in a certain direction. So when this occurs, the atom is said to be electronically polarized, thereby creating an electric dipole. So if we have our molecule here, when we look at it in the presence of this electric field, it's going to make the charges line up and move in opposite directions in relation to this electric field. So this is why it's considered polarized. So the strength of the electric dipole moment, P, is defined by the charge times this vector D, which is the vector displacement between the two centroids of the positive and negative charges of Q. So in certain dielectric materials, polarization may exist in the molecular structure of the material even when no external field is present. So typically in these cases, the polarization on a macroscopic scale is 0. The application of an external field results in torques acting on the microscopic dipoles, as shown over in this diagram here, which converts this into partially coherent polarization along the field on a macroscopic scale. This is known as orientational polarization. Third kind of polarization results from the separation of positive and negative ions in molecules formed by the transfer of electrons from one atom to another in the molecule. In certain materials, this results in a permanent polarization in the absence of an applied electric field. Electrets, when allowed to solidify in applied electric fields, become permanently polarized, and ferroelectric materials exhibit spontaneous permanent polarization. On a macroscopic scale, we define a vector P as the polarization vector. So as the electric dipole moment per unit volume, thus if N denotes the number of molecules per unit volume of the material, then there are N delta V molecules in a volume delta V, so that the polarization vector is then defined as this. So in this case, for each molecule, which we have the number in this volume, we can take the sum of those, and so this will give us N times the polarization, where P is the average dipole moment per molecule. It is found that for many dielectric materials, the polarization vector is related to the electric field in the dielectric simply by this relationship here. And so we've hopefully recognized our permittivity in our electric field, but this new term chi, or chi sub e, this is known as the electric susceptibility. So the quantity for the electrical susceptibility is a measure of the ability of the given material to become polarized, and differs from one dielectric to another. So just like the conductivity for conductors, we have the susceptibility for dielectrics. To understand the influence of polarization in a dielectric upon electromagnetic wave propagation in the medium, we need to return to the case of the infinite current sheet from before, with the condition now that the space on either side of the sheet is now a dielectric medium instead of free space. So we should understand now that the electric field produced by the sheet will induce some form of polarization in the medium. We remember from before that in this case, the electric field only exists in the x direction. Therefore, we can express the polarization in this simplified term of saying that there's just x polarization. And so it's in terms of the electric field in the x direction. Again, where x is it gives a function of position and time. We can now consider an infinitesimal surface of area, which is a differential y times a differential z, parallel to the xz plane. We can write the electric field associated with the area as before. So our electric field then is just the sinusoid defined here, just as was before. So with this definition, the induced dipoles associated with this area can be shown for one complete period, as shown on the next slide. So here's what we have. So as our E field is strongest in this direction, you see that the positive molecules, part of the molecule wants to go in the same direction, and the negative wants to go away from it. As this becomes smaller, this becomes weaker, the polarization becomes weaker. And then, of course, when there's no E field, it's not polarized. And then, of course, the opposite direction goes back and forth. This process can be considered as two plane sheets of equal and opposite time-varying charges displaced by the amount delta, and the x direction is shown here. So here's the displacement value delta, and so we have this Q1, which is this amount of charge here, and then we have Q2, which would just be the negative of Q1 because they're polarized. This now allows us to formulate an equation for the magnitude of the dipole moment per unit volume as this. So our dipole moment then is just our E field times our susceptibility times the permittivity. Since we have a sheet charge that is varying above the surface and an equal but opposite in charge sheet charge below the surface that are both varying in time, this is in a sense a type of current flowing across the surface, since the charges are varying with time. So this is called polarization current, and is defined as this change in charge with respect to time is equal to this value, which is just our dipole moment times our area. And so hopefully you can start to see that current flow is the change of charge in time. So we're used to that being the electrons moving from one molecule to the other, but in this case they're not leaving the molecule, but they're still moving, even though they don't move quite as far. And so this still has the same effect as a type of current flow, or it is a change in charge with time. So if we now divide the polarization current by that differential area, delta y times delta z, and let the area approach 0, we now have an expression for the polarization current density as follows. So again, we take that value we calculated before, divide by delta y delta z, and let that go to 0. We're left with this. And so this is now a new current density that is a result of polarization. We can express the right-hand side as a derivative, right? So if we take the integral with respect to t, we can express this as a derivative with respect to t. And so this lets us rewrite this then as the derivative of the dipole moment with respect to t. Therefore, we can write our current density in vector form then, current density due to polarization, as the partial derivative of the polarization vector with respect to t. This new current density must now be accounted for dielectric mediums in Ampere's law. So remember, Ampere's law said any type of current flow we have to account for it. So we can do that as follows. We can add this new term into Ampere's law. So we have our current density due to conduction. Now we can have our current density due to polarization. Rarely do you have both at the same time, but we want to be able to account for them. And so we can rewrite this then by our definition of what that is the partial of the polarization vector with respect to t. And so now we see we have two terms with the derivative with respect to t, so we can combine those into one. And this gives us this representation of Ampere's law here. So this now allows us to revise our definition for the displacement vector d. So our displacement vector used to just be this part here, the permittivity times the electric field. Well, now we have to take into account the polarization. So now this is the extended definition of the displacement vector in terms of electric field and polarization. So this will be the driving factor when it's a conductive material, and this will be the driving factor when it is a dielectric material. And so we remember before that the polarization vector is defined as the electric field times the permittivity times this susceptibility factor there. And so we can factor out the permittivity and have this 1 plus chi, and that's now defined as this E sub r. And so we now define this relative permittivity. So this epsilon 0 is our permittivity of free space. So when we're in something other than free space, we have to multiply by this second term, which is our relative permittivity. So this adjusts it for not being in free space. So again, this is known as the relative permittivity or the dielectric constant. And so this is something, again, that you can look up in a reference book, or you can Google it to find what it is. And so you can see for air, our relative permittivity is about 1, which is what we'd expect. But then as we start to go into other types of materials, you can see that this value varies, and on this chart it increases. So this relative permittivity is experimentally measured and varies as seen above. So it allows for Maxwell's equations to be used for materials that can be polarized. So for linear isotropic materials, this relative permittivity is independent of the magnitude and direction of the E field acting upon it. This is not true for all materials. So when this is not the case, the material is said to be an anisotropic dielectric material. And so in these cases, the displacement vector and the electric field are related as follows with this matrix relationship. And so the square matrix above, this matrix here, this is known as the permittivity tensor. And so this takes into account, what the permittivity is going to be depending on what direction you're going and where you're coming from. And so again, this is true for anisotropic materials. That means it does depend on which direction you're going as to what the permittivity is going to be. This is actually used quite a bit in optics, for nonlinear optics especially.